Okay, so let's talk about some properties of limits, right? So we've talked about limits, and we've really only looked at limits graphically and numerically, and mostly graphically. It's easiest to talk about them graphically. We're going to move into kind of the next section. Remember that we said there's really three ways that we can evaluate limits: numerically, graphically, and then analytically. And that's the one that you're going to like it better. Graphically and numerically just seems a little hokey, right? You're just making some kinds of approximations based on a graph or a list of values, right? But this way, we're going to get exact answers that are mathematically rigorous, okay? So, start things off here. It says section 1.2. This is out of our regular textbook too. Okay? So we learned that the limit of x as x approaches c does not depend on the value of f at c. The value of, does that make sense? So it was only, and I can't emphasize this enough, this is such a common misconception when you get to calculus, is when you take a limit, just remembering that it doesn't matter what happens when the calculus takes that actual last step, right? It's irrelevant. If we write something like the limit of f of x as x approaches c, x is only approaching c. It never gets there. As soon as the ant gets to c, we're not talking about limits anymore, right? And so for that reason, we looked at some bizarre graphs, like for example, let's just review real quick. What if I had something like this, where there's f, and let's say that's there's my function f. Okay, tell me, what is f of 1? 2. Right? Okay, right?
Why?
Because when x is actually equal to 1, the value of the function is 2. The coordinates of that point are 1, 2. Yeah, this would be a piecewise function, right? Because it's defined for all values of x that are not equal to 1, whatever the equation is that gives us that curve is how the function is defined. But when x is equal to 1, we give it the point, the y value of 2. Okay? So it looked like this. So for example, I'll make one. So what if we did, you tell me what would this look like? If I did f of x equals, oops. That's a piecewise function. How do I read that? What's that telling me? Whoops, hang on. Not equal. Yeah, right. So it tells me that when I input 0 into this function, well, hang on a second. Yeah, that's right. So when I input when I input 1 into this function, when I input 1 into this function, I get back 0, right? Okay, the output of the function is 0 when I feed it a 1. Okay? The output of the function is the line x plus 1 for every value not equal to 1.
And how would that look?
Okay, so let's graph it. Let's in fact color code this. So this will be the red part, and this will be the blue part. What does the blue part look like? 1, 0, right? When x equals 1, the function equals 0. So I get the point at 1, 0, which is right there. How about the red part? Okay, what's the line x plus 1 look like? Okay, so slope of 1, y-intercept of 1. So I'm going to trace it out in light gray, and then we'll only fill in red the parts that we get to keep. So the shape of the curve just looks like that, right? That's the line, y equals x plus 1. But for f of x, I only get to keep the points on that line when x is not equal to 1. So what do you suppose I would do? The hole. I'm going to put a hole at x equals 1. And everything else is included. Okay? So based on this graph, or the definition of the function, take your pick, they go together. Tell me then, what is the, well, I guess you already told me, what's f of 1? 0. 0. There it is, right there. Right there's the point with coordinates 1, 0. Okay, what is the limit of the function as x approaches 1? 2. Yeah. Right? Because that's where the ant thinks he's going to step as he gets infinitely close. Right? But as far as the limit's concerned, he never gets there. Okay? Make sense? Okay. All right, so, oops. Okay, so we get this idea that we don't really care what's happening, as far as the limit's concerned, we don't care what's happening at C. But a lot of times, it's easier than what we just graphed. A lot of times, we don't have a hole in the function. And so it doesn't, we don't have to do anything tricky. In this case, we can see where we think we're going to stand on the function, and it's right there, right? And so that's why the limit of f of x as x approaches 1 is 2. What if I drew a similar function, but it's just a lot easier? It's not a piecewise function. What if I, in fact, just graph the function f of x equals x plus 1? What is the limit of f of x as x approaches 1 this time? 2. We don't have to just rely on only the picture this time. We can see that from the picture. As x approaches 1, we can see that's the point that we're approaching. But what if the graph wasn't so convenient like it is? This time, do I even really need the graph? No, I don't. How come? There's a subtle idea here, but it's really important. What could I do to find out what the answer actually is in this case, if the definition of the function is x plus 1? Substitute 1, right? Now you have to be careful with this. So this is, let me write it this way. The limit of, whoops, instead of writing f of x, I'm going to write it as x plus 1. The limit of x plus 1 as x approaches 1 is equal to 2, pretty obviously, because on our function, f of 1 equals 2. Okay, now why, this might seem like this isn't a big deal, but it is. It's harder, it's trickier than you think. You might sense the answer, but I want you to articulate it for yourself. If I go back to this previous example, and you told me that the limit of f of x as x approached 1 was 2, how'd you get it? Focusing on the point that it approached, right? So we kind of did need to graph this time. Agreed? Okay. This time we didn't. We could use the graph, but it didn't even have to be there, right? Because it's not a piecewise function. And even though the limit is only concerned with the behavior of the function as we approach 1, the difference is, for this function right here, the ant anticipates stepping where he actually will step, right? There's nothing tricky. There's no holes in the function. And so now listen carefully to this. This gets convoluted. The easiest way to answer the question, where does the ant think he's going to step in the bottom example, is just to figure out where he actually does step, because they're in the same place. You get that? Okay. So in some cases, functions are really easy to deal with. There's no bells and whistles and no tricks. The easiest way to evaluate the limit is just to find the actual location of the point that the ant is approaching. We call that direct substitution or direct evaluation. So all we really are doing here, in essence, is we're just plugging in a 1. The limit of x plus 1 as x approaches 1 is just equal to 1 plus 1, which is 2. Okay. Yeah, I get the ant never gets there, but that's the point that he thinks he's going to step on, is the actual point. Okay? Questions, comments? Okay? All right, so if we've got this example where we got these well-behaved functions, we can call them, where they're continuous, right? There's no holes in the function. The easiest way to evaluate the limit is just to plug in the value into the function and see what we get. Because the ant's going to step where he thinks he's going to step. So in the book, they give you some basic limits. Every textbook does this. Rather than just give you these limits and remember them, let's just take a second and think about why they work. So what about this first one? The limit of b as x approaches c is b. Somebody raise your hand and justify for me why that's the case. Okay, give me one. Give me one justification.
Because we're basically drawing just a straight line across.
Okay, so you can think of it graphically.
Yeah.
So the function, that's a good way to do it. B is just some y value, right? And so the function y equals b, let's assume it's positive, is just a horizontal line. Agreed? So it doesn't matter what value, call this one c. Doesn't make any difference. When the ant approaches an x value of c, what y value does he anticipate stepping on? Well, duh. Same one he's on all the time, which is b, right? So you can think of it graphically. What about in terms of direct evaluation, or the trick we just used? There are no holes in this function, and so all we have to do to answer the limit is to evaluate the function. Plug in c. Where do you plug the c? There's not even an x, right? The value of this function is always b, no matter what you plug in. Agreed? Either way, you get back b, okay? What about the next one? The limit of x as x approaches c. Well, you could think of it in terms of a graph, right? We could think of it like this. We've got this line y equals x, and if I approach a value c, what's the height of the function going to be? C, right? Because y is equal to x. It's a line through the origin with a slope of 1. Okay? The other thing you could do, though, you know that the line y equals x has no holes in it, right? So why not just use direct substitution? Okay? What if we plug in x for c? We just get c, right? Same deal. And then, same kind of thing here, right? We could just use direct substitution. Let's just talk about that. So if we plug in c, we know that the function x to the n has no holes in it. It's continuous everywhere, right? Continuous everywhere, so we can use direct substitution. Plug in c and get an answer, okay? Simple. Okay, properties of limits. So I'm going to show these to you, and I'm going to spend very little time talking about them because they will become immediately obvious as soon as we try to do a problem. It just makes sense that this is the way limits have to work. So one limit, scalar multiple. I would have forgotten what that was even called. I mean, I guess I could have thought about it, but you never say these words. These are, you just take limits and you just do this stuff. If I have the limit of b, some constant b times a function, the answer is just going to be b times whatever the limit of f of x is. Notice up at the top that we defined the limit of f of x as x approaches c as being the number L. Okay? So, and later on we'll need this other one too, the limit of g of x as x approaches c, we're going to call the letter k. Right? All we have to do effectively, in terms of algebra, is you just think of this as pulling the b out in front of the limit. And then just take the limit as normal. Multiply by b. Okay? Here's an example. You see how dumb this is? I mean, do you really need to think about this as being 4 times the limit of x? No, you just plug in the 2 and you get 8, right? So you don't, it's kind of a non-issue. Really, you don't need to spend any time on this. Okay, how about this one? The limit of a sum. The way you'd say this in math is the limit of a sum or a difference is equal to the sum or difference of the limits. If I'm going to take the limit of, well, we'll see an example in a moment. I'm not even gonna pause and do an example. What about products? The limit of a product is equal to the product of the limits. I can take them one at a time. Same with a quotient. As long as the bottom's not equal to 0, the limit of a quotient is equal to the quotient of the limits. Power, same thing. The limit of a power is equal to the power of the limit. And we're not going to prove any of that stuff. All right, so this is all in the textbook. It's all on the PDF that I'm putting, that's going to be next to your assignment on Moodle. All this stuff will be available. If you want a picture, take one, but you don't need it. It'll all be there. So let's look then at the limit of a polynomial. How do you think you're going to do this? Just follow your intuition. What would you do there? Substitute. Technically, we're taking the limit of a scalar multiple that's a part of a sum, but you'd never think about it that way. You just take the limits one at a time. You're just substituting is all you're doing, right? So we just plug in 2 and we get 4 times 2 squared is 16 plus 3 is 9. Done. Okay? No big deal. Seems like much ado about nothing really, doesn't it? There's not that much going on here.
If we needed to, we can break it down.
But you won't. You're right. You won't. You won't ever need to.
It's essentially adding new vocabulary to the concept.
Kind of. Kind of. It really is. Kind of. I mean, okay, I shouldn't say that. There's going to be maybe a few isolated cases. I'm going to probably, contrive a way to give you a couple problems where you got to think about this more abstract. But not a big deal. Okay, limits of polynomials and rational functions. What did we say earlier? If we're taking the limit of a well-behaved function that's continuous, right, then we can always just use direct substitution. One thing that's always true about polynomials, any polynomial, they're all well-behaved. And technically well-behaved, we'll talk about this more later. Well-behaved technically means continuous and differentiable. But differentiable is a word that doesn't mean anything to you yet. Well, polynomials will always be able to take limits of any polynomial by direct substitution every time. You don't have to ever worry about doing anything fancy, okay? So for example, well, they don't give us an example. It's too simple. I guess we just did one. What about rational functions? Rational functions, now let's just take a second and think about the behavior of a rational function. A rational function, by definition, is just a ratio of polynomials, okay? Polynomials are defined everywhere, right? They're continuous. What's the only place where a rational function could have some hiccups? Where the bottom equals 0, because you can't divide by 0, right? So as long as you're not at a place where the denominator is equal to 0, it's got to be defined everywhere, right? And so once again, we get to just take a shortcut when we're taking the limit of a rational function. As long as it's not a place where the rational function has a 0 on the bottom, which is going to be an asymptote, or a hole, I guess it could be, then you can just directly substitute. Okay, so let's take this example. If we're taking the example of the limit of x squared plus x plus 2 over x plus 1, as x approaches 1, when x approaches 1, is the bottom 0? Is it? No, it's 2, so we're safe. Plug it in, then you're done. So the answer is just whatever we get when we plug in 1 for all the x's. It works out to be 2. Okay? Radicals, same song, different verse. Oops. Same song, different verse. It's just going to be the same thing. Radicals are going to be, radical functions are defined every place in their domain. And if it's an odd radical function, they're defined everywhere. If it's even, they're only defined where the number inside for values of x, where the number inside is going to be non-negative, right? So in this case, it would have to only be for values where c is greater than 0. Could be equal to, but we're not quite ready for that. That comes in a couple of days. Don't worry about that. Compositions of functions, same thing. This is really handy. So a composite function means you have a function inside a function, right? That could sound like it could be difficult to take limits, but it's not. If g of x is equal to L, and the limit of f of x is equal to f of L, then the limit of f of g of x is equal to f of the limit of g of x, well, that's just f of L, right? All you have to do is take the limit of the inside function and then evaluate the outside function. Here's an example. It's a lot of talking. Let's look at an example. So what if you wanted to do something like this? The limit of the square root of x squared plus 4 as x approaches 0. Technically, that's a composition of functions, right? The inside function is a polynomial, and then you're taking a square root of that polynomial, right? Sounds complicated. It's not. Just evaluate it directly, okay? Just plug in 0 and you get the square root of 0 plus 4 is the square root of 4, which is 2. Done. Okay. So you get the idea. A lot of these are pretty easy, right? A lot of these are pretty easy. Transcendental functions, same thing. That's all the trig functions and the exponential functions and logarithmics combined are transcendental functions. Same deal. As long as you're approaching a number that's in the domain of the function, use direct evaluation or direct substitution. Now, what you might be thinking, what about like a tangent? Tangents have vertical asymptotes. That could be a problem, right? Except, is the tangent function defined at the vertical asymptote? No, it's not. That's not part of the domain, so that's not a limit we're talking about. As long as you're taking the limit at a place that's inside the domain of the function, so it's not a vertical asymptote, directly evaluate. Done. Okay? Okay, so this is getting kind of boring. It's all pretty easy, but it can get harder. So each of these previous examples, do this, so we can just focus on the top. Each of these previous examples, direct substitution worked, right? They were all examples where we could just plug in a value because in each case, the ant anticipated stepping where he actually would step, right? But sometimes that's not the case. What if that doesn't work? Okay, so here's a strategy, and this one is not in the textbook. In fact, I've never seen this in any textbook, but this is good. So you might even want to write this one down. It'll be in my notes, but here's a good way to think about limits. A strategy for finding limits. You're always going to try direct substitution, okay? And either it's going to work or it's not. There's three possible, yes sir?
How do you know if it works?
Okay, here, that's what I'm going to show you. So when you try direct substitution, there's three things that could happen. It works. If it works, then that means you're going to get something that could be written as a fraction. This is not a simplified fraction. The a and the b don't necessarily have to be integers. They could be radicals or other irrational numbers. They could be other things. But we're going to get a ratio of two parts, a numerator and a denominator. Lots of times the denominator might be 1. Right? If we get an answer like 4, well then that's just 4 over 1. If we get an answer like the square root of 3, then that's just the square root of 3 over 1. But you could always write it as in fractional form. Okay? So you're always, if it works, you're always going to get an answer that's in the form of a fraction where the bottom is not equal to 0. Okay? So if you try it and you don't get 0 on the bottom, that's your answer and you're done. Okay? Everything we did fits that category. So that's good news. They're quick and easy, no problem. Other things could happen though. You could get a result like a divided by 0 where a is not equal to 0. So some kind of number divided by 0. Okay? That's a problem. If you get a number divided by 0, that's always going to mean that you get some kind of asymptotic behavior. Okay? And that's a place. What did we say about asymptotes and limits? Limits fail to exist. That's one of the three places that we talked about where they fail to exist, right? And so whenever you get an answer like that, you get a number divided by 0 when you attempt to use direct substitution. For now, at least, the answer is DNE, does not exist. Okay, I'm just warning you, and this is good, it's not hard. We will go further than that, and we'll be more specific. We'll be able to say things like, well, positive or negative infinities, for example. That's a different topic for a different day. Discard that for now. But we will be able to get more specific than this. But for now, if you end up with, when you attempt direct substitution, if you get something divided by 0, something other than 0 divided by 0, you're done. The answer is no limit, doesn't exist. Okay, questions so far? Yes?
What was the one that the graph showed earlier with the line?
Okay, so that's the one we haven't talked about yet. That's the kind where there's a hole in the function, perhaps. Okay, right? So that's the third possibility. So those are the first two. You guys want to see an example of this real quick? Why not? Throw one in. I mean, you'll see tons of these later, but I'll give you one now. So what if you had something like, actually, I might have had one right there, did I? Maybe I put one in. Oh. Oh, I did. Never mind, I gave you an example. Okay. I was smart of myself. So we haven't seen any of those today, but here's an example. If I took the limit of x minus 5 over x plus 2, what am I going to get? Or as x approaches negative 2. If I attempt direct substitution, I get
Negative 7 over 0.
okay, what do you think that's going to look like if I graph this thing? Well, but what's going to be happening then at negative 2? No. Asymptote. Yeah. I'm going to get a vertical asymptote. So there's no limit there. Guaranteed. Done. End of story. So you would enter in Moodle right now. DNE. No, it doesn't exist. Okay? Last possibility, and this is the one we're going to focus on. This is the one that requires a little more thinking. Oops, I forgot to write it down. So you get an answer like this. What if you get an answer like 0 divided by 0? This is what we call an indeterminate form, and this always means more work. This is where you have to do some calculus or some algebra, okay, to get the answer. So that's what we're going to focus on, is situations like that. Okay, so let's take, so let's take an example like this. What if we've got a piecewise function, for example? Let's call it quits for today. Okay.